Okay, Unit 6, Logarithmic Functions and Equations. So Lesson 1, Introduction to Logarithms. So a function is a relation in which each ordered pair has a unique x value. So back in Math 20-2 and 20-1, you might have run into stuff where like you use the vertical line test. So if you had some weird function and you could draw a vertical line and it hit at multiple points, this would be not a function, okay? And similarly, if it was a series of points, but two of the points had the same x value, that would also not be a function. So a function has unique x values. Domain refers to the acceptable x values, and the range refers to the acceptable y values. So here, this will be your horizontal values, and this will be your vertical. That's your y. So we have discussed the characteristics of this exponential function, y equals a base b exponent x. Let us review what we've learned so far. So the a represents the y-intercept. The b represents the base. If b is greater than 1, we have exponential growth. That means it's increasing. It's going to look like that. And if b is between 0 and 1, then we have exponential decay. And that's going to be decreasing. And it's going to look something like that. The y-intercept is always at 0 and the a value. Okay, any y-intercept has an x value of 0. Okay, you need to just know that. Okay, any y-intercept, the x value is 0. Because if we look at the graph, all right, a y-intercept means it's on the y-axis. Okay, so any of these points and any points in between, all of them fall at x equals 0. So any y-intercept, the x value is 0. So let's graph y equals 2 to the x to refresh our memory. So on our graphing calculators, if you go to y equals, and we're going to go 2 exponent x. Okay, and if we hit graph, you get something like that. Our window settings on this are a little funky. It's super squished. So on your notes package, it's going to go up a little bit quicker. So if x is 3, our y value is 2 cubed, which gives us 8. Okay, so if x is 3, so there's 3, and we go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's the point that we get. Okay, and if x is 2, then our y value, or corresponding y value, is 4. So we go to 2, which is 1, 2, and then up to 4. 1, 2, 3, 4. So we're doing a point at 2, 4. And if x is 1, our y value is 2. And if x is 0, our y value is 1. There's our y-intercept. And if x is negative 1, we get 1/2. And it keeps going down. So 1/4, 1/8. And if you connect this, all these dots, you're going to get your exponential growth. Okay. Now recall that there is an asymptote at the x-axis. Okay. The line's never going to cross it. It's going to get very, 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 very close, but it's never going to cross it. So the domain is x such that x is an element of the real number system. That means it's every x value has a point. And you could actually draw in a whole bunch of other points. The line is made up of an infinite number of individual points. Okay, so every x value there is a corresponding y value. So the range, remember we said there's a horizontal asymptote at y equals 0, which is the x-axis. So the range is everything that's above the x-axis. So it's going to be y such that y is greater than 0, and y is an element of the real number system. The y-intercept is 0, 1, and the x-intercept there is none, and that's because of the horizontal asymptote. Okay, so the horizontal asymptote tells us some information there. So a logarithmic function is the inverse of an exponential function. The inverse of a function is found by interchanging the x and y values. The graph of an inverse function is a reflection in the line y equals x. Well, that's a whole lot of information, but let's graph this stuff. All right, so given this function, x equals 2y, we are going to graph the inverse of it. So if x is 8, what exponent, oops, it's not going to be y, what exponent with base 2 would give us 8? And if you're thinking 2 cubed gives us 8, you are correct. So our y is the exponent. All right, well, let's do another one. If x is 4, how would we get 4 in terms of base 2? Okay, and that's going to be 2 squared. So 2 squared is 4. So the exponent is 2. All right, and we can follow this relationship. 2 cubed, 2 squared, 2, 0, 2, negative 1. Oops, missed 2, 1 there as well. And we can fill out this table of values. So 2 and 1, and 1 and 0, and 1/2, and negative 1, and 1/4, negative 2, and 1/8, we get negative 3. Now those are pretty similar to the last values we got, but just kind of in reverse, right? We're substituting the x and y values. Interesting. So let's try and graph this thing. So x is 8, and our corresponding y value is 3. So we're going to go to 8, 1, 2, 3, 4, 5, 6, 7, 8, and 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. So up there. Okay. And then we're going to get 4 and 2. 4 and 2. And then we get 2 and 1. And we get 1, 0. Now we get half and what do we get? Half and negative 1. And then we get closer and closer to the y-axis. So let's connect our points. Well, what do you notice about this graph? Well, it kind of looks similar to the other one, but just a little different. Okay, so this is a graph of x equals 2 to the exponent y. This is our y-axis. This is our x-axis. So the domain, first of all, let's talk about the asymptote. There's a vertical asymptote at the y-axis. So it's going to get close to the y-axis, but it's not going to cross it. So there's a vertical asymptote at x equals 0. So that means our domain is x such that x is going to be greater than 0, not equal to 0, just greater than 0, and x equals xer. That means, if I'm going to highlight this, highlight yellow, that means for every x value, there is a valid solution. Okay. The range, well, this is increasing very slowly, but it is, and it's also decreasing very quickly. So our range in this case is y such that yer. Every y value is going to be valid in this scenario. There's no y-intercept because it doesn't cross the y-axis, and the x-intercept is going to be at 1, 0, similar to what we had with exponential growth, but just in reverse. For the function y equals 2 exponent x, the inverse is x equals 2y. The inverse of an exponential function is called a logarithmic function. In general, y equals bx is exponential, has the inverse function x equals by. So we can form this relationship here that the log of base b of x equals y, and x equals the base of b to the exponent y. There's this relationship, and you can go between each form. Okay, they're equivalent to each other. So the value of the logarithm is simply the exponent of the corresponding exponential function. For example, x equals 3y is the same as y equals log 3x. You'll notice that the base, if I can get precise highlighting here, the base is the lowercase 3, okay, for the log function. Now the exponent, y, is the outcome of the log. And the outcome of our exponential function here, x, is the x that's there. So 9 is 3 squared. It's the same as 2 equals log base 3 of 9. Now the bend method. So, get my pen here. The base with the exponent equals the number. That implies that log b n e. Okay. Now I've also seen some people, when they're in log form, they do a 7. So they start at the base to the exponent equals the n. Okay, so the base to the exponent equals n. All right, so if you are either of those ring a bell, great. Sorry, not ring a bell. If either of those sort of make sense to you, you can use them. So express in logarithmic form. So we saw that the base is going to be the lowercase part of the log function. So the 8 can go there. Now the exponent is what it equals, and the x goes there. 3 to the negative half equals 1/9 means that log base 3 of 1/9 equals -2. 243 equals 3 with an exponent 5. So the base is the lowercase part of the log. So you can start there. And then you swap the different parts, okay? So before we had the 3 with the 5. Now we have the 3 with the 243. And so that's going to equal 5. All right, we get log base 10 of 0.0001 is equal to the exponent, -4. Back up to the top here. Log base 5 of 125 is equal to 3. Log base 12 of 1 is equal to 0. Log base 49 of 7 is equal to 1/2. And this one's a little trickier, but we get log base half of 1/8 is equal to 3. The last one, BAC, so we get log BCA. All right, express in exponential form. So again, what works for me is starting at the base, going to the exponent, and there. So we get AT equals M, starting at the base, boom, boom. So 3 equals 27. 7 equals 1. 27 to the 1/3 equals 3. start at the base, 2 exponent 5 equals 32, start at the base, 6, 1 equals 6, start at the base, 3, negative 1 equals 1/3, start at the base, so 9 squared, oops, negative 2, there we go, equals 1/81. Awesome. So then we're going to move on to evaluating these logarithms. So we have this equaling some value x, all right? And in all of these, you're actually going to have to set them equal to x. So 3x equals 81. Well, if we go back to our expressing with common bases, 81 is equal to 3 with an exponent 4. So therefore, x must equal 4. 10x equals 1,000, while expressing things with the common bases. 10x will equal 10 cubed. So therefore, x must equal 3. 27 exponent x is equal to 3. So common bases, we get 3 to the 3x is equal to 3, 1. Therefore, 3x must equal 1, and x equals 1/3. 5 to the x equals 25. 25 is the same as 5 squared. Therefore, x must equal 2. 2 to the x equals 16. 16 can be expressed as 2 exponent 4. Therefore, x must equal 4. 5 exponent x is equal to 625. If we express 625 in terms of base 5, you'll get 5 exponent 4. Therefore, x must equal 4. All right, 10 to the x is equal to 1,000. Expressing 1,000 in terms of, 1 over 1,000. Okay, let's look at this 1 over 1,000. Let's express 1 over 1,000 in terms of base 10, so that's 10 cubed. And if you remember, an exponent in the denominator is equal to a negative exponent, therefore x must equal negative 3. Where are we here? Okay. Here we have to convert root 5 into exponential form. So 5 exponent x is equal to 5. Now the root symbol is equal to 1/2. Therefore, x must equal 1/2. Okay. 3 to the x is equal to 3 exponent 5. Therefore, x is equal to 5. Perfect. That one was nice and easy. All right. 2 to the x. So again, 2 to the x equals 7. Therefore, x must equal 7. All right. 10 to the x is equal to 10 to the 4. Therefore, x is equal to 4. X to the x is equal to x cubed. Therefore, actually, we shouldn't use, that's bad math. All right, we've already given x a position. So let's call this some other variable, like m. xm equals x cubed, therefore m equals 3. That way we're not applying the same variable in multiple places. All right, 8 to the x is 4. So let's express both of these in terms of base 2. So 2 cubed is equal to 2. So 3x is equal to 2 squared. Therefore, 3x is equal to 2, and x is equal to 2/3. Beautiful. Okay, 5 cubed is equal to x. So we can just evaluate that. What is 5 cubed? Well, 5 cubed is 125. And remember, we're expressing our answer in terms of x, okay? Don't write 125 equals x. We're expressing it in terms of x, not in terms of something else. All right, log 8 is equal to 1/3, so we get this relationship where we get 8 1/3 is equal to t, and you can just evaluate that on your calculator. 8 with an exponent 1/3, so t is equal to 2. Again, expressing our answers in terms of the variable. X cubed is equal to 64. Right, and we can take the cube root of something. All right, so if we take the cube root, or the other way to think about it is raising it to the exponent 1/3. So you can do that same thing to both sides, and you're going to find out that x is equal to 4. Now you could think about the number 64, and I know that 4 cubed is 64, but whatever way is going to work out for you there. Okie dokie. This is equal to x, so 7x is equal to 7 and 1.3. Therefore, x has to equal 1.3. All right, m exponent 4 is 625. Again, you could try and think of some number that if you raise it to the 4th power, you're going to get 625. You can also do this little trick where you raise it to the exponent 1/4. And that you can just evaluate on a calculator, and you're going to get m equals 5. If you don't have a calculator on this question for whatever reason, you know that it's going to be some number to the exponent 4. So 2, 4, we already know is like 16. 3, 4 is like 81. 4, 4 is whatever it is, 256. And 5, 4 gives us our answer. Okie dokie, we're getting a little bit more tricky here. 8 to the negative 2/3 is going to be, again, just evaluate that right on your calculator. And you're going to get y is equal to, you'll actually get 0.25 if you do it on your calculator. Why don't we? 8 negative 2, let's do it. Okay, so 8, and then you press the little exponent button, which is just under the clear button, and then you're going to have to do bracket negative 2 divided by 3 and close your brackets. And if you hit enter, you get 0.25. Now you need to be able to recognize that that is 1/4. If you're unsure or you're drawing a blank, you can press the math function, and option 1 says frac. So if you just hit frac, you're going to get 1/4. Or if you type in 0.25 math, it gives you a fraction in lowest terms. Okay, so if you're ever stuck, but you have this graphing calculator with you, any decimal, 0.324. If you ask your calculator to turn a decimal into fraction, it'll give you the fraction in lowest terms. Okay, 0.5, math, frac, 1/2. Okay, back to the lesson. All right, 3 to the x is equal to 27 negative 1. So common bases, we can turn 27 into a common base. And we're going to get 3 to the x is equal to 3, and then 3 times negative 1. So therefore, x must equal negative 3. Oh, I never solved this one over here. 1/4. All right, x0 equals 2. Well, anything to the 0 exponent is 1. So this is not possible. All right. This one, put a little star by these bad boys. Okay, these are a little tricksy. Following the same rule, there's our base to the exponent is going to equal log 2/5. All right. Now, what else we got here? So we get, where's my pen? 2 to the x is equal to log 2 to the 5. Now, if we just change the form of what this is this is going to be log 2x. Okay. And we end up with something like this, where we get log base 2 of x is equal to log 2, 5. Okay. Actually converting this back to logarithmic form and leaving this one just as it is. We get log 2 to the x is equal to log 2 to the 5. And from there, you can see that x is going to equal 5. Okay. All right. 9x is equal to log 5, 25. So we have our base. Let's convert this. We get log 9x is equal to log 525. Now, log 525 actually just equals 2. We can evaluate that. So we get log 9x is equal to 2. All right, if we just go over the side here, log 525 is equal to x. We get 5 to the x equals 25. 5 to the x equals 5 squared. So it follows that the whole thing is equal to 2. So from here, we can go 9 squared equals x. Therefore, x must equal 81. Okay, those two are a little tricky.